monotone property. So for example, yeah, so it is different with the if a support count, if ABC is 10, for example, then any subset is, for example, AB, if of course it is can be maximum than 10 or greater than 10 or equal, sorry, yeah, always greater than equal to 10. But for rules, it's different condition. Yeah, so for ABC, then D, it can be larger or it can be smaller. That's why if we have like this, we have to calculate all confidence, each of them. Okay, but confidence of rules generated from the same item set, it has anti-monotony property. Yeah, if it is from the same item set. This two is not from the same item set. Yeah, the first one is from item set A, B, C, D. The second one is A, B, D. Okay. Okay, but this one is from the same item set. Okay. So for rules generations, let's say we have this is rules which has low confidence. Then if this rule is from the low confidence, then the next one will also have the low confidence. So if we found out, for example, oh, this rules in this branch is have a low confidence, so we don't need to create this one. Yeah, no need to spend time to calculate this one. Okay. Okay. Sorry. This is we only talk about a priori algorithm. So all of these steps that we just discussed, these are all belongs to a priori algorithm. Of course, there are many other algorithms. Okay. Then algorithms and complexity. Yeah. Fact, there are so many factors can affect the complexity of a priori. First, choice of minimum support threshold, and then dimensionality of the data set, size of data set, and average transaction width. Okay, let's see one by one. So, if we choose minimum support, of course, we will have more frequent item set. Yeah. In that case, of course, our computational time will be longer because we will calculate more items, frequent item set. Okay. Okay. Yeah. So in that case, if we think that in our data, we have too many items, too many transactions, so maybe we can consider to use a high minimum support instead of low minimum support. Okay. And of course, dimensionality of the data, number of items of the data set, it higher number of items, the computational time will be also higher. Yeah. More space is needed to store support count of each item set. Yeah. If the number of frequent item set also increase, and the computational time also will be increased. Size of database, runtime of algorithm increase with number of transaction ports. Average transaction width, the transaction width increases the maximum length of frequent item set, of course. And then number of subset in the transaction increase with increasing computational time. So transaction width is this one. how many items in one transaction. More items, of course, the computational time will be much longer. So you can imagine if we apply association rules in one big supermarket, then of course it is in terms of computational, it will be very complex. Okay, so for practical suggestion, in this case, we can use many strategy. For example, let's say before we apply association rules, uh, my suggestion is it is better for us to determine what is our goal. For example, if we are only, let's say, yeah, in one, let's say, for example, we have supermarket, and then we know that why the sales for one specific item, let's say, for example, fresh product, for example, uh, sales for fresh product is very low, for example. So in that case, the goal of our research here is we only want to focus on fresh product. Okay, let's say fresh, or okay, for example, like this. For example, in this case, uh, in our store, we found out why sales for eggs is very low, for example. Yeah. So maybe instead of analyzing all transactions and with many different items, first we have to filter our data, for example. So here we've only focused on transactions including include eggs. So in our case, for example, transaction 1 we can eliminate, transaction 3, transaction 4, transaction 5 we can eliminate this. Maybe other transaction including eggs we can include in our database here. So in this case, we can reduce the computational time or the computational complexity by reducing number of transactions, because we only want focus on a specific type of item. In our supermarket, for example, if we only focus on fresh product, so we can eliminate all transactions which not include the fresh product. It can help. What else? We also can reduce the items, the number of items, if we think that it is not necessary to analyze. We're not interesting to analyze that item. We also can eliminate it. Okay, this one we've only finished from one algorithm, a priori algorithm. Then there is another, there are so many algorithms actually, but for now I will introduce you another algorithm, which is the FP-GROW algorithms. Okay, actually basically it's quite similar with a priori, but it has different steps, different algorithm. Okay, so in FP-GROW it allows frequent item set discovery without candidate generation. Yeah, so for a priori, focus on candidate generation, candidate for frequent item set, and then candidate for pruning, for example. But for FP-GROW, it's tried to find out the frequent item set without generating candidate generations. Okay, so for FP-GROW algorithm, this is the main step. It tried to build a compact data structure, which call it the FP3, and then it will pass over the database and extract the frequent item set directly from the tree. Okay, let's see. Okay, for example, basically they will develop or construct what they call it FP3. Okay, so to construct the FP3, they will read the database like this, pass over database, yeah, one by one. So 1, 2, 3 until all database. So for example, this is the root of the tree. Okay, start from null. After reading the transaction 1, because transaction 1, they call it A and B. They bought A and B. Okay, so first they construct one branch. A equal to 1 means that because the first item A is now in this case after transaction 1, only one transaction by item A. Okay, and then after A also B, A, B. Okay, so A, the number here is the counter, and this is the counter. This is also the counter. A equal to 1, B equal to 1, because this is only after transaction 1, after reading transaction 1. Okay. Then after transaction 1, we go to transaction B. Transaction 2, sorry. Transaction 2, the first item is B. Okay. But our current tree is the first branch is A. So we have to build another branch here. So like this, B. Okay. B equal to 1. Counter is 1 here. And then after B, C, D. Okay, so B, C, D. The counter is 1, 1, 1. Yeah, of course, because 1, 1, 1. Yeah, transaction 2. Okay, and then go back to the next transaction, transaction 3. It's only transaction 3, A, C, D, E. Okay, the first item is A. So we go to this branch. So in this case, because go to this branch, so the counter will increase 2. Okay, but the next item is C. So here is B. So we have to make another branch here. This one, C equal to 1. Okay, C, and then D and E. Counter still 1. Hey, why I put E here? E counter still 1. Okay, so for all transaction like this. So for all transaction, we develop the tree. So that one before we finish until 3, we continue to 4 ADE, ADE, A. After so the transaction 4 here I use different color. Transaction 4. First item is A, sorry, so go again to this nodes. So this node will increase into 3. Okay, and the next item is D. So now we have B and C, not yet have D. So we have to build another branch. This D. D equal to 1. Okay, and E. E equal E equal to 1. Okay. Next transaction ABC. So this one we can go to BC. A or here. So again go to this branch. So A increase into 4. B, this one, A, B, B increase to 2. And then we have C equal to 1. Until all of this transaction. Yeah. So if this transaction, for example, this transaction already has the branch, so we just increase the counter. But if there's no branch, so we can build the new one. Okay, always build the new one. For example, if we consider transaction 8, ABC, let's see, in current situations, we already have A, B, C. So no need to make a new branch. Just increase the counter here. So this one will be 5, this one will be 3, this one will be 2. Yeah. Okay. Finally, at the end, we will have this tree from all 10 transaction, we will have these three. Yeah, if you want to evaluate, for example, validate, for example, where this a equal to 8 come from. So we see from the transactions which one has the uh, item A. So should be there are 8 transactions. 1, 2, 3, 4, 5, 6, 7, 8. That's why. Okay, and why B here they have 5? Because there should be 5 transactions here, which involve A and B. So let's see, A and B, 1, 2, 3, 4, 5. Okay, yeah. So this is the FP3. Okay, so remember to build this tree, we go through the transaction one by one. If the items is not yet have the branch represent the item sequence, we can make a new branch. But if the branch is already have in the tree, we just increase the counter. Okay. The size of FP3 is typically smaller than the size of the uncompressed data because many transactions often share a few items in common. Yeah, of course. Okay. Best case scenario, all transactions have the same set of items. Okay, so all transactions have the same set items. So for example, transaction 1, A, B, C. Transaction 2, A, B. Transaction 3, A, B, C. All the same item set. So in that case, we only have null, A, B, C. Always. Only one branch. But the worst scenario, every transaction has a unique set of items. Of course, then we will have so many branches. Okay. The size of FP3 also depends on how the items are ordered. So here, before we apply FP3 algorithms, we have to make sure that the order are always the same. So make sure, for example, at transaction 1, ABC, transaction 2, AB, make sure that this one recorded as AB, not BA. Okay. Yeah. So actually, these two are the same, right? But we have to make sure that the sequence of the items should be the same. For example, make it all the transaction is in alphabetical order. Okay. And then this one, after we have the tree, for example, this is the complete tree. Then we have to extract a frequent item set from the FP3. Basically, the algorithm is bottom-up algorithm from the leaves to the root. So from the last one to the root. Yeah. First, extract prefix pad for subtree ending in an item set. Okay. So for example, this one, this is the result of the extraction from this complete tree. Okay. So here we can have, for example, this one. This is the last one. Maybe for example, they start from this one. Okay, and then containing pads containing node E. Okay, so focus on containing node E. Sorry, not this one. Containing node E. So will be 1, 2, 3. E containing node E. Okay, and then we focus on from the final leaves containing E, go up to the branch, to the root, sorry. So we see it should be this one, and this one. Okay, this is the first extraction. Then the second one is the item D. Okay, we talk about item D. Now the note with item D. So we focus on the final leaves which contains of D. So should be this one, this one, this one, this one, and this one. So then we take from D the final leaves to the root. So it will be like this, this one, and this one. Okay, the second extraction contains node D. Then contains node E. Also, this is A, B, C, D, E is the items. Okay, continue to node C. Okay, node C is this one, C, finish, only 3. So here, and here. So it becomes like this. Yeah. Then we continue until all items. Extraction for all items. Okay. Then we have like this. We have, because we have 5 items, so we have 5 extraction. Okay. And then from each tree, extraction tree, we can generate frequent item set. For example, let's try to, maybe we can, wait. Yeah, this one, for example. Let's start from the easiest one, A, because A is the very simple one. So A, from this extraction tree, we have the item, the only item set here we can develop is A. Yeah, so we have A. One item set consists of A. Then for containing node B, here suffix B, let's see, we have this in this branch, we have B, and from this branch, we have AB. So that's why we have B and AB. Okay. From extraction of the node containing node C, like this, we have, let's see, we have BC, okay. And then we have, what else? This one, ABC, from this ABC, and then also we have AC, and of course, we have the items that give C. Okay, also D. Yeah, so we search one by one all the branch like this until all of them. Okay, so this is the frequent item set founded from the FP3. So it's
Dr.
different.
Farah.
Yeah.
Why isn't A, B, C, D considered only up until 3 items?
A, B, C, D. Which one?
From the path containing node D,
Not D. Okay.
there
Which
is
one?
A, B, C, D, the
Okay.
longest path. Yeah.
Okay. So here, A, B, C, D. A, B, C, D. A, B, C. Oh, C is not included. Okay. So A, B, C, D. A. Oops. So here, basically, I think I missed one table. So before this, we actually have to find out first the item set. For example, you just mentioned like A, B, C, D here, for example. But then we have to calculate the, again, after we list. I think I should have like this. Before this table should be A, B, C, D, E, and then all the lists like this, all of the branch, and then again we calculate the support count. And finally, after we have the minimum support, then we have the frequent item set. Okay, so originally it has A, B, C, D for D. Let's say this is D, A, B, C, D, but maybe this one less than the minimum support, so it's not included here.
Oh, okay. Thank you.
You're welcome. So basically the FP growth is to avoid this one. Compared to the a priori, the basic idea is to avoid candidate generation, because the FP growth, maybe they think that for candidate generation it already still takes so much time, so they eliminate candidate generation. Okay. Beside FP grow and a priori algorithms, they also introduce us, for example, a compact representation of frequent item set. So sometimes based on our database, we can directly find out which one is the frequent item set. Okay, for example, let's see if this is the data set. We have 15 transactions and we have 30 items. We have 30 items. Okay. So for example, some the minimum support threshold, this is the minimum support, is 5. Okay. So which one is the frequent item set? Okay. So in this case, we can say that, because let's see, you can see that it's already record, and the representation of the data set is already like this order, so we can see directly, oh okay, so this one A1, oops, this one is the frequent item set, and then this is frequent item set, C is frequent item set. Why? Because there are at least 5 transactions, 1 2 3 4 5, which at least 5 transactions by item A1 until A10 together. Also for B1 and B10, at least there are 5 transactions by the same item, B1 until B10. Also from C1 until C10, the same item. So sometimes with different representation of the database, we can get, or it can help the computers to find out the frequent item set faster. Okay, so they call it a compact representation of the database. So basically, many researchers do so many ways to help us identify a frequent item set faster and more efficient. Okay. I also would like to introduce you with what we call it maximal frequent item set. So maximal frequent item set, an item set is maximal frequent if it is frequent and none of its immediate superset is frequent. So let's say this it is the maximal frequent item set, I can say that it is the last item set which has the frequent. So after that, if we grow more, then it becomes the infrequent. So for example, like this. AD, I call, for example, AD. See, AD is frequent item set. But from AD, it became ABD, ACD, and what else? ADE. Which one again? This one, AD. AD, AD, AD. Okay, so AD is a frequent item set. Okay. But all superset of AD is infrequent. This is infrequent, this is infrequent. So AD, we call it maximal item set. It's like a border. We call it border. Because after this, more than if we put any items after AD, then those item set will become infrequent. Okay, so AD is maximal item set. For example, again, ACE. ACE, the superset of ACE is ABCE and this one, ACDE. Both of them, they are infrequent. So ACE is maximal frequent item set. Okay. Why we need to identify this? Usually we will need this information to understand also this is the last frequent item set. We don't need to further expand this item set. Okay. With the compact representation of the database, we also can determine or we can identify maximum item set directly. Yeah, for example, like this. This is A1 until A10 is a maximum frequent item set. Why? Because once we add, let's say A1 until A10, and then we put A1 until A10, and then we plus B1 becomes one item set combined like this, then it will be less than 5, the support count. So if we combine this one with B1, then it becomes infrequent item set. Okay, so that's why A1 until A10 is the maximal frequent item set, because if we add any other items, whatever the items, then it will become infrequent. Okay. Also the same thing with B1 until B10. B1, if item set only contains B1 until B10, like this, there are 5 transactions, include B1 until B10. But if we add any one items in item set B1 until B10, for example, we add C10, for example, then the count for this item set will be less than 5, and it becomes infrequent item set. So B1 until B10 is a maximal frequent item set. Also for C1 and until C10, this one. If we add one more items, any items, then it will become infrequent item set. So C1 until C10 is a maximal frequent item set. Okay. Okay, this one, another example. So the black one means that that transaction by items A. So this is 0101. Okay, so what is if the support threshold, the count is 5. So what is the frequent item set? So here we have to find out which one items which has the frequent by include in at least 5 transactions. together. For example, from here we see that item A only buy 1, item B no one buy, item C only buy by 3, D only 3, E only 4, F 1, 2, 3, 4, 5. So that's why frequent item set is 5 if the support count is 5. So the frequent item set is F. And then F is also the maximal item set. Why? Because if we add F by any other items, then it will be infrequent. For example, F and I. So let's see how many, there is no transaction by item F and I. How about F and E, for example? F and E, then they are 1, 2, 3, 4, only 4 transactions by item F and E. So it will be infrequent. So that's why the maximal item set is F. Okay. How about if the threshold for the minimum support count is 4? So we can see which items uh, appear in at least 4 transactions. So we see from here item E 1, 2, 3, 4. Okay, so it will be item E, and F also. So this one 1, 2, 3, 4. Yeah, so it will be E and F. Okay, how about J? 1, 2, 3, 4. Okay, J itself, it is also the frequent item set. Okay, yeah. Oh, sorry. Also for the all combination. So E itself, F itself, J itself, and E and F. Okay. But the maximal item set, it is only E, F, and J. Why? Because we see that for E, the superset of E, it can be E and F. It is also the frequent item set. So E, of course, it is not maximum item set. F also is not maximal item set because the superset of F, for example, EF, is also frequent item set. Yeah. Again, for example, how about the minimum support is 3? So minimum support is 3, then we will have, first we calculate items appear in at least 3 transactions. So this one, C, D, E, F, J. Okay. C, 1, and then D, and then E, and then F, and then J. Okay, what else? How about this one? So it may be 3, C and D, C and D and E, C and D and F, also the same. Yeah, frequent item set. Okay. Yeah. I put it like this, all subset of C, D, E, F. So it is the same like this. C, D, E, F, C, D, E, F we have, and then C plus D. So it can be C, D, and C, E, C, E, and we also have C, F. Yeah, so any subset of, again, finally we have C, D, E, F. Any subset of C, D, E, F is also frequent item set. Yeah, plus J. Okay, maximal item set. Okay, let's see. From all of these, which one has the combination maximum 3? For example, like this. So C, D, E, F. Okay, but if we include another one items, then it will become infrequent. So that's why CDF is the maximal, also J itself is the maximal. So here, the way of illustrative of how we can find out frequent item set and maximal item set without a priori or without FP grow. We just use compact representation of the database. Yeah, this one also. Yeah, maximal item set A, B, C, and for if the count of 5. Yeah, the same way from the previous slide. Okay. We have now closed item set. So we have maximal, and we also have closed item set. Closed item set, an item set X is closed if none of its immediate superset. So immediate superset means that, for example, this is AB. So immediate superset will be A, B, C, A, B, D, for example. Yeah, has the same support as the item set X. Okay. So for example, item set A, superset of A, superset of A, it can be AB, AC, AD. Okay. Then from the transaction, we can calculate the support count for A is 4. Oh, is 4 here. Support count for AB is 4. Support count for AC is 2. AD is 3. So here, is it a closed item set or not for A? Let's see. Item set A is closed if none of these 3 has the same support. But in our case, AB has the same support with A, the same 4. So A is not closed item set. So not closed. How about B? Let's see. B, the superset of B is AB. And then what else? BC. And then BD. Okay. From the data, the support count for B is 5. AB is 4. BC is 3. BD is 4. So here, item set B, the support count is 5, and none of these has the same support. This is 4, 3, 4. None of these has 5 support. So B is closed item set. Let's continue with A, B. Okay. Superset of AB is A, B, C, A, B, D. Any others? A, B, C, A, B, D. Okay. Count for AB is 4. ABC is 2. ABD is 3. Okay, so none of superset of AB has the same support of AB, has the same support with AB. So AB have 4, ABC has 2, ABD has 3. So no same. So AB is closed item set. Okay. How about ABC? Let's see. ABC, superset of ABC is only A, B, C, D. Yeah. ABC, the support is 3. ABCD is 2. Okay, so A, B, C. ABC. Okay, so ABC. Sorry, ABC is 2. ABCD is 2. Okay, so this one is not close item set because the same support. Yeah, how about ACD? ACD, superset is A, B, C, D. Okay. ACD support is 2. ABCD support is 2. They have the same support. So ACD is not closed item set. Okay. So closed item set is if the superset has different superset have different count, support count. Okay. Okay, so this one is the we call how we mapping the maximal and closed item set. Okay, we see from this if this is the transaction ID we try to identify, put here. Then we see if, for example, we set the minimum support is 2, then let's see these two, for example, the support is 2, for example, CE, yeah, and then the superset of CE, this one count is 1, this one count is 1, so CE is closed. Okay, and then is it maximal or not? We see that 2 is the minimum support, so we see here the support of CE is 2, so this is still frequent, but after CE support is 1, this one support is 1, so after CE it is infrequent, this is infrequent, this is infrequent, so that's why CE is closed and maximal item set. Also happen with DE. Okay, how about C, D, E? Let's say for example C. Yeah, C support count is 4, and then after superset of C, let's see, this one AC is 3, and then BC is 3, and then this one CE is 2. So the support is, there's no superset has the same support with C. So C is closed. However, the superset of C is still frequent. This is frequent. The superset is still frequent, frequent, and frequent. So C is not maximal because the superset is still a frequent item set. Okay. Yeah. So this is we can use information about which one is maximal and which one is closed to focus on that item set instead of other superset other item set. Yeah. Okay. Oops. This one we know this already, the closed item set. Yeah. Okay. This one also the item set, the closed item set is C is the closed item set. Also for CD is also the closed item set, C and CD. Okay, this is another example from the compact representation. We can know is it directly. So the closed item set is 3, C, this one, 1, 2, this one, 3, and also CDE, CDE, because they are 2. Okay. This is another example. Yeah, this is the mapping of what is the frequent item set, closed item set, and closed frequent and maximal frequent item set. Okay. Okay, now how we evaluate the pattern. So this is also important because of course if our objective is to implement association rules, then all those algorithm, of course they have already, we can found the code already, yeah, but we have to know what is inside the code. Then after the implementation, we have to understand the result. So here we know that how to do the evaluation. Okay, association rule algorithms can produce a large number of rules. That's one that we have to consider, yeah, because they can produce very large number of rules. However, we only interest to some rules that can give us some meaningful rules. Okay, so to identify what is the meaningful rules, of course we can use like support or confidence. Okay, but we also can have other rules evaluations. For example, given x and y or x, y information in the to compute interestingness. So besides support and confidence, we also can compute the interestingness of the rules. Okay. Before in classification, I guess you know already what is contingency table, you know Gini already, you know entropy already. Yeah. So for example, we use analogy of the contingency table to compute the interestingness of the rules. Okay. Let's say we have x and y like this, and then we mapping this one if f11 is if x then y, and this one f10 if this one is like this, if x then no y, this one if no x then y, this one if no x then no y, this one if x then y. Okay. Before we only consider confidence and supports. Okay, so we can use confidence, but there is a drawback of confidence that we have to be aware. Okay, for example, from the data here, customer buy tea and coffee, yeah, and then finally we can, of course there are many other items, but for this case, for this example, we only consider tea and coffee because we want to identify or we want to evaluate the rules. If a customer buy tea, then he will also buy coffee. Okay, so here is the contingency matrix. Okay, so from this data, the confidence of rules tea then coffee is 0.75. Where I get this number? Because like this, they are from this transaction, there are 1,000 transactions, and from 1,000 there are 150 people, customer buy tea and then buy coffee. So the support count for xy is 150. Okay, and then how many customer buy t x? Yeah, don't forget for confidence, the formula is support count of x and y divided by support count of x. Okay, so here our x is t, coffee is y. Okay, so from this data we see that xy is this one 150, and then the x, the one who buy t, is 200. Okay, so the confidence is 150 divided by 200. It is 0.75. So confidence is 0.75, which is quite a high number. So we have 75% confidence that if one customer buy tea, it is also will buy coffee. Okay, but let's see. Is it really true like this? Yeah, the rules seems reasonable, of course. But then from this data, we can see that the probability for customer to buy coffee is 0.8. It is quite high. Okay, so no matter the customer buy tea or not, finally they will buy coffee. Yeah, so this confidence value 0.75 becomes not very clear. Yeah, because no matter the customer buy tea or not, 80% of them will buy coffee. So this rule, although the confidence is 0.75, but we see like even though they will not buy tea, like this, they also will buy coffee for this one, 0.18125. So the rules become not meaningful. Yeah, because uh, even though they buy tea or not, they will buy coffee. Yeah, so sometimes we have to be careful with confidence. Okay. Again, for example, tea and honey. If people customer buy tea, then they will also ask for honey. Okay, same one, the same like before. So confidence of this rule. So we calculate confidence support count of tea and honey divided by confidence of tea. So let's see, tea and honey is 100. Tea is 200. So it's 0.5. Okay. But, oh, sorry. Yeah. But again, then this with confidence 50%, which may mean that drinking tea has little influence whether honey is used or not, because it's not quite high, only 50%, and the confidence of these rules. But, for example, number of people or probability of customer buy honey is only 0.12. Yeah, quite small. So tea drinkers are far more likely to have honey, for example. Yeah. So again, we have to be careful with the confidence. Okay. So what kind of rules do we really want? Of course, we want the confidence should be sufficiently high. Okay. To make sure that the people who buy X will more likely to buy Y than not to buy Y. That's why for this case, tea and coffee, we should be careful. Yeah, tea and coffee, confidence is 0.75, which is quite good. But not tea and coffee is also high. Yeah, so be careful. In some cases, maybe tea and coffee is high, but tea and not coffee, if it's also high, then these rules becomes meaningless. Yeah, so we have to be careful. Okay, this one is happen with this tea and honey. Okay, confidence confidence of X then Y should be greater than support of Y. Okay, otherwise the rule will be misleading, because having X actually reduces the chance of having Y in the same transaction. Yeah, so if this one also maybe happen. So we have to be careful. Okay. Okay, this is the statistically relationship between X and Y. Basically, this is just basic statistic. Yeah, like this. This is conditional statistic. Yeah, the basic one. Okay. We know that if you only consider confidence, there will be some drawbacks of confidence. So that's why there are also some other measurements we can use to identify our rules. And these measurements actually depend on based on the statistic, because basically the association rules is the similar like conditional statistic. Okay. So for example, there is what we call it lift or interest. This one, lift or interest. Let's say we use interest. Okay. The interest is, this is the same example before we use confidence to calculate. Okay. And then, how if we calculate using interest? So the interest of rule coffee and tea, then by coffee is, this is the example, dxy dx divided by dy. So probability of xy divided probability x and, oh sorry, multiply by y. Okay, so probability of xy, this one, tea coffee, 150 divided by 1000, so 1 2 3, so 0.15. Probability of x is t, so here 200 divided 1000, 0.2 times probability of y is coffee, so 8, so it should be 0.8, so it is 0.9375. Okay, this is the note. So if the interestingness is less than 1, then they are negatively correlated. Yeah, so we have to be also careful. Although the confidence is quite high, but they have negative correlations. So negative correlation is, if buy tea, they also will not buy coffee, or if not buy tea, they also will buy coffee. So different by this one, reverse of tea by coffee. So we have to be careful. Yeah. Okay. There are also some others measurements. Yeah, we can try. All of these help us to calculate to help us to solve drawbacks of confidence. You can choose which one. Of course, each of them has drawbacks. Each of them has the advantage. Okay. For example, we have cosine. Let's see. We compare interestingness and cosine. Yeah. We have two different rules. This is P, and if P then Q, and this one is S then R. Okay. Then we use these equations, yeah, to calculate. Okay, F11 is like this. I think I put this before. This one. So F11 is in this one. F plus 1 is here. As F1 plus is this one. N is this one. Yeah. So when we calculate which one? Okay. IAB, this is the interest. IS is cosine. Okay. Wait. Oh, sorry. This is interest, not IS. It should be like this. Here. Okay. Sorry. Typo. Oops. Oh, okay. So this is interesting, interest, and this is cosine. Yeah. This is F11, this is N, this is F plus 1, this is F1 plus. Okay. So we using this equation, we calculate. We then compare rules P, this one P, then Q, and this one R, then S. We compare, for example, this is the confidence of P, then Q. This is the interest of P, then Q. And this is the interest of R, then S. Oh, sorry, S, then R. S, then R. S, then R. This is S, then R. This is also the confidence of S, then R. Okay. This is the cosine. We calculate already, and the higher is better. So for cosine is higher is better. For interesting, we have one. One means independent. Greater than one is positively correlated. Less than one is negatively correlated. So here, this one all positively correlated. This one also positively correlated. And from the number, we can see that R and S is more positively correlated than P and Q. Okay. Compared by cosine, P and Q, this one is stronger than R and S. So this one, using three measurement, the result can be different. Yeah, so we have to make sure which one measurement is more suitable for our result. Or we can say that, oh, okay, for according to the cosine, P and Q is stronger than R and S. And according to the confidence, P and Q is also has the higher confidence than P and than R and S. So we prefer rules P and Q. Okay. Okay. This one, property under null additions. So we also have to be careful when if in our data set there are too many null addition, null zero equation, no zero value in our database. Okay, and also, for example, the property under row or column scaling. So for example, we from one database, for example, we get the rules already. For example, if using max, using mass, and then COVID free, for example. Yeah. But then if we duplicate let's say duplicate the number of transaction, number of people here, for example, we hope that although we scaling up the row or the column, then the rules should also be still apply. Okay, should be independent of the relative number of COVID positive and COVID free subject. Yeah, so this is the property. Of course, different measurements will have different property. Yeah, so if there is no property is applied, then for example, then we have to recalculate again the measurements. Okay, this is just for information, like many real data set have skew support distribution. Okay, so this is support count. This is the rank of the item. So maybe the support distribution of a retail data set, for example, it can have skew support distribution. few items with high support and many items with low support, usually like this. This is the correlation between support account and the rank of item. Okay. Effect of support distribution. It's difficult to set an appropriate minimum support threshold. If minimum support is too high, then sometimes we miss the item set involving interesting rare items. Yeah. Sometimes, because mostly the, for example, let's say we know the a priori and FP grow, both of them based on minimum support. But if we set the minimum support is too high, then they will filter our item set, they will filter our rules. So sometimes, and we know from them from before the previous slides, sometimes the confidence is not represent meaningful rules. So we have to be careful. Do not set a minimum support too high and only consider confidence. Yeah. Okay. But if the minimum support is too low, then of course it is computationally expensive because we have to deal with a large number of item sets. Okay. Yeah. This is the pattern of the minimum support and the sorted items. Okay, to deal with that, we can consider using the cross support. Okay, so this is the equation of the cross support. Yeah, this one. For example, confidence of calf if calf by caviar then by milk is very high, but the confidence of milk and by caviar is very low. So therefore, the cross support we use the minimum of confidence, minimum of this and minimum of this. This is the cross support. Okay. To avoid patterns whose item has very different support, we can also have edge confidence or all confidence. Yeah. Sometimes in the code, sometimes they already give us the edge confidence. Yeah. To calculate the edge confidence. Okay, this is also the measurement of the edge confidence. Okay, cross support and edge. This is the property of cross support and edge confidence. Okay, what else? Yeah. Okay, I think I can skip this. This is the hypercyclics. Okay, and this one, if you want to get the code, you can get from this link. This is the package of the association rules. Yeah, using this. Okay. Maybe I can give you this. You can try it at home. Yeah, how to get this. And this is the benchmark data set of the for the association rules. So I think I have to show you how to prepare database for association rules. How we save the database for association rule is like this. Make sure our data is like this. This is all items that we want. For example, item A, B, C, D, E, all items. And this is the transaction ID, 1, 2, 3, 4, 5, until all. And this is the binary value. 0 means if transaction 1 doesn't buy item A. 1 means if transaction 1 buy item B. Okay. So this is the database if we want to apply this one. For example, I use FP Grow. Okay. But if our data is still like okay, transaction 1 is by item B, C, D, transaction 2 by item A, B, C, and still in the shape of list like this, in this case, we have to use this one, transaction encoder. So transaction encoder is to transform our data set, which is in the form of the list like this, into a matrix, a binary matrix like this. Because this package is only can run, it's required the database in the form of binary matrix like this. Yeah, so if we use transaction encoder to like this to transform from the list into the binary matrix. Okay, I think this finish. Yeah.
The package would be transaction encoder.
Sorry, the package is what?
The transaction encoder. Like we have to download transaction encoder.
This one. You have to set this package MLX10 preprocessing MLX10. So the package for association rule is MLX10. This one, MLX10. Yeah, the name is MLX10. Okay. In that package, they have a priori, fpmax, fpgrow. You can explore. Okay. Any questions? Okay, no questions. If no questions, again, I'm sorry, I have to give you assignment, just a small assignment. I just need you to try the program for the association rule. So you have experience in doing association rules. You can use any data set. You can, there's many data benchmark data set for association rule. You can use any data set, and then you apply. You can try this code for your assignment, and you can see. Try to play with the number of minimum support, and you can see what happened if you change the minimum support and what happened with the rules. You also can try to use make this program give you another measurements for the rules. For example, matrix, they call it the matrix. In this example, for example, the matrix I use confidence, but they also can give us different metrics. Yes, so you can play with the package. So for the assignment is I just ask you to try package of the association rules. Yes, so you can next time if you really want to do the research using association rule, you have experience already using the basic one. Okay. So just a very simple assignment. I wish you can submit your assignment in 1 week. So next week, I hope you can submit that. Okay. And use any benchmark data set. So this will be the third assignment, individual assignment. Okay, so this is the third assignment. Okay, due to 1 week. Okay, any questions? I want to share different. Wait. If no questions, I think I want to show you our schedule. I just find out that May 1st, another holiday. So I have to change our class. Oh, wait, I haven't shared this one.